Good afternoon, everyone. Questions while we wait? Good afternoon, everyone. Come on
This is really happening. We're not scared of hunger. This is really happening. Nobody's working, nobody's shopping. Take the money on, take the money on, take the money on.
All right, how are we doing? Questions? Anyone? How are we doing with the simplex method? At least for the standard maximum problem. Let's do one more example. Shall we? Questions before we do so? We're good? I've uploaded new web work assignments. I'm sure you've seen those, right? Might just be the one. All right. The idea, as we saw last time, is to introduce slack variables to transform the inequalities into equations. So let's do that. Let's introduce S1, S2, and S3, which will transform these inequalities into equations, namely where all the xi's and sj's are bigger than or equal to 0. And we're trying to maximize this for minus x1, minus x2, minus 4x3, minus 5x4, plus z is equal to 0. So let's transport this into an array known as the simplex tableau. Right, where we'll reserve the first column for the x1, x2, x3, and so on. S1, S2, S3, Z, and the constants. So here's our initial simplex tableau. Make sure you have that. Does everybody have this? Questions? You know what to do. We next need to find a pivot. Let's do it. The pivot lies in the column with the most negative number in the last row. So pivot's going to live in this column. Pivot cannot be 0 or negative. So it's either going to be 1 or 5. How do we choose it? Smallest quotient. 115 divided by 1 versus 200 divided by 5. Pivot is not 1, but 5. Smallest quotient, right? People? 5? Great. All right. So let's use this 5 to get rid of that one. Row 4 plus row 2 for row 4. And then maybe a 1 over 5 row 2 for row 2. All good? And that was painless enough. We're done. Well, we're actually, no, we're not done. We're not done. We haven't finished clearing out the column, but after that, we'll be done. After that, we'll be done because there will be no negatives in the last row. That'll be it. Final simplex tableau, we're able to read off the solution. X1, right? So final simplex tableau, because again, no negatives in the last row. We're done. X1 does not have a leading 1. X1 is 0. X2 does not have a leading 1. X2 is 0. X3 does not have a leading 1. X3 is 0. X4 has a leading 1. X4 is 40. This is S1. S1 is 75. S2 does not have a leading 1. S2 is 0. S3 has a leading 1. S3 is 50. And finally, Z is 200. Does that make sense? Let's look at our original inequalities here. 40 times 5 is 200. Looking good. Looking good. There it is. How are we doing here? Questions? Questions about the simplex method as it relates to the standard maximum problem? Why did we do row 1 minus row 2? This was our pivot, so we have to clear out the column. right? We had just turned this one into a 0 right here. That is not sufficient, right? That is not the entire pivot operation. We have to clear out the column. We have to finish it. Yeah, but there it is. All right. Well, it's all well and good if we have the standard maximum problem. But what if we don't? Right? What if the objective function is not to be maximized? What if the inequalities are going the wrong way? I mean, we've seen that occur in the graphical method, and that was not an issue for us there because we could just graph and everything's fine. But here, we just have the standard maximum problem that we can solve using this. Before we define another problem, let me start by defining the transpose of a matrix, as this will be useful in the next definition, and moreover, it appears on the web work. I think we had defined it already, right? Yeah. This is the answer. We're done. Absolutely. Right, we're done because this is the final simplex tableau. There are no negatives in the last row. So one pivot operation did it. That was it. And it was much longer to write down the question than to actually do the work here. I think we had defined transpose, had we not? In case we hadn't, I mean, I'm almost 100% sure we did, but we had, right? Yeah. Well, in case somebody missed it along the way, give it an n by n matrix A. We define as transpose, denoted a transpose to be the m by n matrix whose rows are the columns of A. Or vice versa, whose columns are the rows of A. And let's illustrate with an example. If you have A like this, the transpose, the first column becomes the first row. The second column becomes the second row. This used to be a 3 by 2, well, not used to be, it's still a 3 by 2 matrix. Its transpose is a 2 by 3 matrix. Let's take another example. take a moment to work out the transpose here. What is the transpose? First row becomes the first column. Second row becomes the second column. Third row becomes the third column. And once you know it, this is exactly what you started out with. B transpose is actually the same as B here. And of course, it's not always the case, right? But sometimes it is. Very nice. So, I mean, the transpose has some nice properties. Namely, if you have two matrices, the transpose of a product is the product of the transposes in the reverse order. Very much like the inverse. Right? We show that the inverse of a product is the product of the inverses in the reverse order. It's the same for the transpose. Right? The idea is, how do you calculate this? You take a row of A and you multiply by a column of B. But when you take the transpose, the columns become rows and the rows become columns. That's the idea. Questions here? This property works for all matrices indeed. Yes. As long as the product is defined. Yeah. Let's consider another nice property. If you take a matrix and you write its rows as columns, and then you write its columns as rows, what are you going to get? In other words, if you take the transpose twice, think about it. Right? You take A, you write its rows as columns, and then take its columns and write it as rows, then obviously you get the original matrix back. Absolutely. And observe that if you take any matrix, let A be M by N, then A transpose is N by M. So the product A transpose is N by N, A is N by N, so this product is always defined. And similarly, A times A transpose is N by N, and A is M by N, right? These agree. Both of these products are always defined. Yep, they're always defined and they're always square. Observe, furthermore, if you take the transpose of this matrix, well, the transpose of the matrix of a product is the product of the transposes in the reverse order. So this is going to be A transpose times A transpose transpose. But A transpose transpose is the original matrix A. So the transpose of this matrix is just itself. Isn't that nice? And I'll let you do the other one. But the transpose of this is just itself again. How are we doing? I think we had defined the notation Aij, right? So how does that relate to the transpose? If you have this matrix Aij, the transpose, you write the rows as columns, or the columns as rows, right? I corresponds to the rows, J corresponds to the columns. So if A is Aij, then its transpose is going to be Aji. Exactly that. Yep, very nice. All right. What's the point of rediscussing the transpose here? We have defined the standard maximum problem for a linear programming problem. Let us now define the standard minimum problem, or standard minimum form. A linear programming problem So a linear programming problem is said to be in standard minimum form as opposed to standard maximum form, right? I think you can guess where we're going with that. If the objective function is to be minimized, two, all variables are non-negative. In other words, the yi's are bigger than or equal to 0. And 3, all other constraints have the form A1y1, A2y2, all the way to AN bigger than or equal to B, where B is bigger than or equal to 0. So, essentially the same as standard maximum problem, but the exact opposite. You're minimizing, variables are still non-negative, and the inequalities are going the other way. What's very interesting here is that associated to any standard minimum problem is an associated standard maximum problem whose solution is the same. So associated to any standard minimum problem is something called a dual problem. So it's an associated standard maximum problem which has the same solution. So instead of solving the standard minimum problem, we're going to find the dual problem, the associated standard maximum problem, and we're going to solve that in the way that we know. How is this done? How is the dual problem found? Using the transpose. Let's illustrate. All right. So here, first of all, let's convince ourselves that this is in standard minimum form. The objective function is to be minimized. the variables are non-negative. And all other constraints have the form of a combination bigger than or equal to numbers that are themselves bigger than or equal to 0. I mean, Britain is asking the obvious question, right? I mean, are minimum problems always written in terms of y versus maximum in terms of x? There's no need for that. Doesn't have to be. It makes it easier to distinguish, but the truth is that it doesn't need to be given in terms of y or x. Right, so the point here is that we have a standard minimum problem. We're going to find the standard maximum problem by rewriting these things in a matrix. Right, so first inequality, 2y1 plus 3y2 is bigger than or equal to 15. 5y1 plus 6y2 is bigger than or equal to 35. I have made a slight mistake. Forgot to account for the I'll be fine. Uh, 1535 and W 2y1 plus 3y2. Here we're just finding the dual problem. Right, we're not introducing static variables or anything of that sort. We are just finding the dual problem, right? Because we have a standard minimum problem. I'm suggesting that, well, here's the double E, right? 2y1 plus 3y2. I'm just suggesting that we're going to rewrite this in a standard maximum problem by taking the transpose. If you take the transpose of this matrix, what do we get? First row becomes first column. Second row becomes second column. Third row becomes third column. And now let's rewrite this as a standard maximum problem in the same way that this gave rise to that. This is going to give rise to 2x1 plus 5x2 less than or equal to 2. 3x1 plus 6x2 less than or equal to 3. And we are maximizing the function 15x1 plus 35x2 subject to this. And x1, x2 greater than or equal to 0. Right, so we had a standard minimum problem. We built this matrix, took the transpose, and retransformed that into a standard maximum problem. So instead of solving this, we're going to solve that. Well, because it should be a standard maximum problem. And you know standard maximum problems, the objective function is to be maximized. Variables are non-negative, and the inequalities, a combination less than or equal to something positive. Exactly that. It's a maximum problem. So let's solve this now. By introducing slack variables which transform the inequalities into equations So this is the dual problem, absolutely. Exactly, and as Asma suggests, the idea is to transpose the matrix to get a maximum problem. Exactly that. We use this idea of duality to convert a minimum problem into a maximum one. And we have fit minus 15x1 minus 35x2 plus z is equal to 0. So let's put all of this into a simplex tableau. Excellent. Do we have to convert the answer we get for the max back to a minimum problem at the end? Usually you do, yes. Unless the question was just asking what is the maximum. Can z have a negative number? No. I mean, right, we are assuming x1 and x2 are bigger than or equal to 0. So this combination here will not be negative. Do we forget about the w? We don't. We don't. Well, let's do this and we'll see the relationship. Let's find our pivot. And I think we all know what the pivot is. You tell me. What is the pivot in this case? Why are we getting the pivot wrong? 5, thank you. Right, it's the smallest quotient. First of all, pivot lives in this column. So we had the column right. 2 divided by 5 versus 3 divided by 6. So 0.4 or 0.5. The 0.4 is the smaller of the two. 5 is the pivot. Is that clear, everyone? And that's the danger, right? I mean, you want to be careful. It's not 6 divided by 3, but 3 divided by 6. All right, there's our pivot. Let's use that to get rid of the 35, and then we'll change it into a 1. Row 3 plus 7 row 1 for row 3. And then row 1, 1 over 5 row 1 for row 1. Here we go. I want to use the 1 to get rid of the 6. Row 2 minus 6, row 1 for row 2. So this minus 6, 15 minus 12 is 3 over 5. Fifteen minus 12 is 3 over 5. Excellent. Excellent. We're not done, right? We still have a negative in the last row. You know what to do. Pivot lives here. 2 over 5 divided by 2 over 5 versus 3 over 5 divided by 3 over 5. 2 over 5 it is. Thank you, Annie. Right? I'm sure you've noticed that both quotients are the same. They're both 1. Exactly. Topmost. Topmost it is. So let's change, what do we want to do? Yeah. Let's change that into a 1. I didn't want to erase this. Let me not erase it. I'll try to leave it there. We'll change that into a 1. 5 over 2, row 1 for row 1. All right. And let's use this 1 to clear out the column. Row 2 minus 3 over 5, row 1 for row 2. And row 3 plus row 1 for row 3. Blake, as suggested, if you have 2 of the same most negative number, it's the leftmost and the bottom. And how do we select the pivot if they're equal? You take the topmost. Of course, this is just an arbitrary rule, right? But it's a rule so that you don't get lost in a loop and you don't just undo what you did before and get in trouble. It could have just as easily have been the lowest. And if you keep working with that, that would have been fine. Or it could have been, I mean, whatever. But it's a rule, so it's an arbitrary rule so that you don't get lost in the process. So topmost, if 2 or more are equal. Leftmost, if you've got the most negatives 2 or more times. We're doing this operation. First row remains unchanged. So this minus 3 over 5, so there's minus 3 over 2. This minus 3 over 5, I want to say minus 15 over 15 minus 1. That can't be right. Minus 15 over 10. Minus 15 over 10, or minus 3 over 2. Does anybody have that? Is that correct? Well, this is our final simplex tableau. Thank you. This is our final simplex tableau, so we should be able to read off the solution. Right, you'll recall that this is x1, x2, s1, s2, z. x1 has a leading 1, x1 is 1. x2 does not, x2 is 0. S1 does not, S1 is 0. S2 has a leading 1, S2 is 0. And Z has a leading 1, Z is 15. Does this make sense? If x1 is 1 and x2 is 0, that's 15. And 2 less than or equal to 2. 3 less than or equal to 3 works very well. Works very well. There it is. Now, Rosalie asks the good question, because that was not the original question, right? The original question was minimized. Let me rewrite it there. Minimize 2y1 plus 3y2 subject to what? 2y1 plus 3y2 bigger than or equal to 15, and 5y1 plus 6y2 bigger than or equal to 35. That was the original question we had. So now, how does this answer relate to the answer we want? To the answer for the standard minimum problem? Well, the z is going to be the same. Right, so the solution is the same. Z is 15, so W is 15. It's the same answer. What about y1 and y2? Certainly, they don't correspond to x1 and x2, right? Because no combination of 1 and 0 is going to give you 15 here. Instead, they correspond to the last entries in the slack variable columns. So S1 and S2, last entries were 15 over 2 and 0. Y1 is 15 over 2. Y2 is 0. I'll let you observe how that works. Yeah, why is that? An obvious question, right? And to answer that, I don't have a good answer for that. We'd have to look at the proof, and the proof is way beyond us. Right? So the Z and the W correspond. They are the same thing. And the question arises, what are y1 and y2? Well, they certainly don't correspond to any combination of x1 and x2. You will find y1 and y2 in the last row of the slack variable columns. So last row of the slack variable columns. No, don't leave your answer in terms of x1, x2. This is the question we wanted to answer. So you should give your answer in terms of y1, y2, and w. This is what you're looking for. How are we doing? Do we want to do another one? All right. There you have it. So again, we're going to find the dual problem by transporting this into a matrix, taking the transpose. Right, so 2, 3, 4, 45. 1, 5, 2, 40. And 4, 7, 9. Yep. Javier, that's right. This is the solution. We were asked to minimize W subject to these conditions. The minimum W is 15, And it occurs when y1 is 15 over 2 and y2 is 0. Instead of bigger than, it's less than, do we subtract s? I'm not sure what your question is there. Here, you mean? I mean, here we did not introduce slack variables, right? Instead, we found the dual problem. Right? I mean, here there is no slack to pick up, in fact. Right? We want to make sure that the left-hand side is bigger, not less. Let's rewrite the dual problem. In the dual problem, we wish to maximize z equals 45x1 plus 40x2, subject to x1 plus x2 less than or equal to 4, 3x1 plus 5x2 less than or equal to 7, and 4x1 plus 2x2 less than or equal to 9, where the xi's are bigger than 0. Right, this is the dual problem. Let's introduce slack variables to transform the inequalities into equations. And bring the x's to the other side, you know the deal here. So we're going to set up our simplex tableau. Let's set up our simplex tableau. 2x1, 1x2, s1, s2, s3, z. There we have it. We search for the pivot. The pivot, which lives in the last column, or first column. And Easy to see that the pivot is 2. Thank you. Nice save there. 2 indeed. Everybody comfortable with the 2 as the pivot? I'm sure you are. Let's, what do we want to do? We want to use the 2 to get rid of the 4 and then maybe change it to a 1. Row 3 minus 2, row 2, row 1, minus 2, row 1 for row 3. And then 1/2 row 1 for row 1. And now let's finish that up by using this 1 to clear out the column. Y is plus Z and not minus Z. Well, I mean, it's Z equal to this. So all I'm doing is I'm bringing these to the other side. In the midterm, you have to indicate which number is the pivot. You should. You really should. You should, so that it's clear to the marker what you're actually doing. So here, 1 is my pivot still, right? We're using the 1 to clear out the column. Row 2 minus 3, row 1 for row 2. And row 4 plus 45, row 1 for row 4. Can I squeeze that in? Let's try. First row remains unchanged. This minus 3. This minus 3, so 10 minus 3, 7. This minus 3. And this plus 45. This plus 45. Minus 35 over 2, is that right? You can tell me. 45 over 2. 0, 0. And 90, 90. Is that correct? It's fine to do so just by circling it, absolutely. Why are we modifying rows other than the last? Isn't the goal only to get rid of the negative numbers on the bottom? That's our ultimate goal, but remember that, right? I mean, if I just did the last row, then I would want to choose another pivot, not having played around with these 2 rows, so things would go south very fast. Right? We're finding the smallest quotient, and that becomes of crucial importance because that keeps track of how large things can get. And if you don't get rid of these two entries, when you come to figure out your next pivot, everything's going to be off. Right? As in this case here. We need to find the next pivot. The next pivot is going to live in this region here. And what is it? Well, it's this divided by that, or this divided by that. And it's clear to see that this is now the new pivot. If we hadn't gotten rid of it, well, it would have turned out to be the same. Maybe coincidentally. Let's use that to get rid of that. That works out nicely. Row 4 plus 5 row 2 for row 4. And then maybe a 2/7 row 2 for row 2. We're adding 5, so 30/2, which is 15. 5, 0, 1, and 95. Let's use that one to get rid of the 1/2. Row 1 minus 1/2 row 2 for row 1. What was the pivot in the one before? It was 2. And now it's 7/2. Let's finish that up. 1, 0. This minus 1/2. So 7, 10. 5/7. I want to say 5/7. Somebody please check that. Minus 1/7, 0, 0. And 13/7. Ten over 4 or 5/7. Thank you. There it is. Final simplex tableau, right? No more negatives in the last row. We're good to go. X1 is 13/7. X2 is 2/7. S1, S2 is 0. S3 is 1, and Z is 95. that was the solution to the standard maximum problem. I've rubbed it off, but you can check. You can check. Well, we can kind of check here, right? Z was 45x1 plus 40x2. Those are big numbers. So big. So big. Well, I'll let you check that. But what we're interested in was the W. So W and the Z will agree, and the Y's correspond to the entries of the slag variable business. So 15, 5, and 0. Let's recall. I'll copy it back down. What did we have? 4, 7, 9. Does that make sense? You get 60 plus 35 is 95. Very nice. Very nice. Everything works out very well. How are we doing? Questions? Anybody? No? All right. So practice this standard minimum problem by finding the dual, and consequently practicing the standard maximum problem, right? And we'll go ahead, Asma. Asma has a question. I believe there are a maximum of 7 web work assignments. What's the last column after S3? 0, 0, 0, 1. Corresponding to the Z, of course, right? Corresponding to the Z. Asma is saying for the second matrix on the right, there was no pivot because in the same column as before. We hadn't finished doing the pivot operation, right? In the pivot operation, you want to change your pivot to a 1 and clear out the entire column. Now, we didn't change it to a 1 immediately because we saw that we had a nice combination of 2 and 4. We didn't need to introduce fractions first. So we use this 2 to get rid of that 4, and then we change it into a 1. This is still our pivot. We're not finished clearing out the column. Why was the final row 1 modification done? Because that's what a pivot operation is. You're changing the pivot to a 1 and you're clearing it out. You cannot stop before you've cleared out the column, even if you no longer have any negatives in the last row. Right? Even though you don't have any more negatives in the last row, you still have to finish clearing out the column. Because only then you'll be able to answer the question, state the solution, right? Here, x1 has a leading 1, so x1 is 13 over 7. If you hadn't cleared it out, x2 would not have a leading 1. So you would be tempted to say x2 is 0, which is incorrect. So the pivot needs to be the only non-zero term in its column. Correct. Column, David, right, instead of row. But yes. And that answers Sarah's question as well, right? Why did the pivot change again? Because we were not in the final simplex tableau. We still had a negative in the last row. If you still have a negative in the last row, you're not done. Unless there was no way to choose a pivot, right? Unless the numbers in this column were all zeros or negatives. As you know, the pivot cannot be zero or negative. So if this had been the case, then there would have been no solution to the problem. But it is not the case. We can choose a pivot. So we continue. How are we doing? Questions? Is that good for everyone? Very good. So thank you all for coming. You guys have a good weekend, and I will see you next week.